Dear friends, welcome to this electrical engineering knowledge sharing channel, AMP power system. We are discussing short circuit calculation, and under this section 7, we are continuing this workshop. In this session 7, we have already completed 5 videos starting from 55 to 59, and in those 5 videos, 3 videos for symmetrical short circuit current calculation. Rest two videos, that is video number 58 and 59, we have discussed about the unsymmetrical fault current calculation basic procedures. First 58 video number 58, we have discussed the basic symmetrical components resolution to calculate the asymmetrical fault current, and second videos we have shown how the various load impedance can be dissolved or can be decomposed in positive, negative and zero sequence impedance. Using those, and we have also said that this positive, negative and zero sequence component of impedance is the basic module for the calculation of asymmetrical short circuit current calculation. Now, with this positive, negative and zero sequence component of impedance, that is, we have shown that positive sequence components impedance Z1, negative sequence component Z2 and zero sequence components Z0, along with the current component I0, I1, I2, and voltage component is V0, V1, V2 for any one of the phase. Any one of the phase we can resolve these three parameter of the electrical parameter into these components. But when this is for one phase only, suppose this is a phase. So A phase, what are the impedance that we can dissolve into these three? A phase current we can dissolve into these three components. A phase voltage can be dissolved into three components. Similarly, B phase and C phase we also dissolve into the same ways, and then what will be the components will be coming. Suppose A phase, B phase, C phase, when you take the only zero sequence component, suppose we are taking the zero sequence current, then A phase zero sequence current, B phase zero sequence current, C phase zero sequence current in the same direction, that is this way. Then A phase positive sequence current, B phase positive sequence current and C phase positive sequence current, these are all three balance system. Similarly, when you go to the negative sequence components, this will be also the balance, that is A phase, it is B phase and it is C phase. When you go to the negative sequence components, that is I2 A phase, it will be I2 B phase and I2 C phase. This way we can dissolve the asymmetrical component of current into these three sequence component, and each set of sequence component balance to each other. That means it is like a symmetrical components now. So when we calculate the symmetrical current, we use the balance system. Now this unbalanced system is converted to the balance system using this zero sequence, positive sequence and negative sequence components, and each set of components to balance each other. So this is a balance each other. This positive sequence components of three phase are balanced each other. Negative sequence component of current is also balanced each other. This we have seen, and then we have find out how this positive, zero and negative sequence component of impedance for the various type of loads, how it is, what is the configuration of those, that also we have seen. And we have said that that's positive, zero and negative sequence component of impedance of the various type of loads, that is a rotating equipment, non-rotating equipment, transmission line, transformers, will be considered as a basic master block to calculate the asymmetrical short circuit current due to single line to ground fault, double line to ground fault or double line face to face fault. This we have already discussed. Today video we will find out how these components are related to the single phase to ground fault short circuit current, double line to ground fault short circuit current and line to line fault or phase to phase fault short circuit current. That will be our today's workshop. So first we will calculate the short circuit current calculation for three phase power system when there is a single phase to ground fault takes place. So let us draw a single phase three phase system. Suppose there is a power system, there is a generator, then suppose there is a transformer, then there is a bus bar. From there suppose there is transmission line, there is a transformer, then suppose there is another bus bar, then there is suppose there is a motor load. So this type of power system is there. So if we want to calculate this power system, for this power system, it is I have drawn a single line. If we consider this way three phase, there will all be three lines. Suppose there is a fault over here or fault over here to single phase to ground fault. In that case, how we can calculate or what will be the expression for the single line to ground fault current that we will drive today. So this entire network, suppose this is our a network, we can remove from here. Suppose we have a three-phase network. Suppose this is a three-phase network, and this network contain all these components. What we have shown, this inside this box, you can say there is a transformer, there is a generator, there is a transmission line. All this is a three-phase network or three-phase power system. You can say this is a three-phase power system network or power system. Now from the three phase, there are three phases are coming. Like these are the three phases, and there is a neutral, right? I have consider this is a three-phase 4-wire system. There is a neutral which is grounded. So this is our neutral. So this is our A phase, this is a B phase, and this is a C phase, this is a neutral. So this three-phase network is running normally. Suddenly, all of the phase, suppose this phase is got grounded. Okay. That means grounded means these are the same potential. That means this is connected over here. Then there is a fault current will be flowing. Now before fault, there is a voltage over here. There is a phase to ground voltage. So that voltage is VAG. There is a voltage over here VBG, and there is a voltage over here VCG. Right? And there is a current flowing through here. There is a current flowing through. There is a current IA. There is a current IB. And there is a current IC. It is a before fault. Before taking this fault, this is the condition. System was running normal. System was balanced system. And the moment fault takes place, immediately this phase start feeding current to the fault. At that time, this only feeding the load current. But this load current IB and IC is so small with comparison to the fault current. Suppose this fault current is IF. This with respect to IF, this current VA, IA, IB and IC, when before the fault, whatever the load current was flowing, the load current we can neglect when we consider the fault current. So in the calculation of fault current, one of the assumption is load current, or that before the fault, whatever the current flowing through the network, that fault current should be considered zero. That means IA equal to 0, IB equal to 0, IC equal to 0. That is the load current. The load current is when fault takes place, then this load current will be considered 0. But before the fault, this load current has a certain magnitude. That is not neglected, but the moment fault takes place, immediately the fault current magnitude is so high. IF is greater than IA or IB or IC. Therefore, this IA, IB, IC, when we are calculating the fault current, IA, IB, IC can be considered 0. So during the fault current calculation, when we calculate the fault current, load current is neglected or net current shall be considered 0. So when this fault takes place, what is the condition? Then we can consider B phase current. There is no current in the B phase. That means B phase current equal to 0, and IC, C phase current equal to 0. A phase current that converted to IF, that become IF. So we have to calculate this IF. We have to calculate this IF with respect to this phase voltage. But when this voltage, when the fault takes place, this phase voltage, there is a voltage, there is a voltage, and there is a voltage. But this voltage before the fault, this 3 voltage was balanced. Before the fault, this voltage VAG, VBG and VCG was balanced, three-phase balance apart from each other to 120 degree, and the magnitude is also equal. But the moment take place, then VBG may be longer, VCG may be longer, and VAG may be shorter. So this voltage become unbalanced. So under that condition, as this current is, there is no fault current in this phase, B phase and C phase. So only the I fault, C phase will be following the current. That current is IF. And suppose there is when the fault takes place, if we consider the fault takes place through a fault impedance, suppose there is a fault impedance here. That fault impedance is, suppose ZF, the fault impedance. Then the current flowing through this ZF, this fault impedance due to the earth, when it is going to the earth, this, suppose this is a cable is connected over here. So cable is going to earth through some impedance. That unknown impedance we call it ZF. Or there is some, when the neutral is connected to the ground, it could be connected through a ZF. Suppose if it is connected through a intentionally one resistance is connected to the network, then that also could be considered over here. So that impedance we have considered the earth impedance or the impedance in the neutral part, that is ZF. If ZF is at earth impedance, in that case you see the VAG current, what we can write down, VAG, this the current which is flowing due to this voltage, VAG voltage, which is unbalanced. VAG, VBG, VCG both are all are unbalanced to each other. This unbalanced voltage VAG which will produce the current IF. That IF current, simple Ohm's law, we can calculate IF equal to this voltage VAG by ZF. We can simply calculate this way. This is my IF fault current in terms of VAG and ZF. Now, as this voltage is unbalanced, we don't know the magnitude of this voltage. That's why we have to find out this current with respect to the fault voltage, and during the fault, whatever the magnitude of the voltage, that voltage in terms of the this impedance, Z impedance in terms of the sequence components. How we can calculate this? From this expression IF equal to, that is equal to IA, you can say another way, this is equal to IA, and IB, we know already IB equal to 0, IC equal to 0. Now we know that the phase current or sequence current, there is a relation between phase current I phase, that equals to how much, that is A inverse I sequence components. We have already seen this relation before. Phase current I phase current equal to A inverse. What is A? A equals to, we have seen, A inverse equal to how much? 1/3 of this matrix A square A. This is the matrix, A inverse matrix. So if we calculate, if we want to this phase current, we know the this is not the, this is equal to AS. We have already calculated AS. This is equal, this is AP. Yeah? We have seen already the sequence current IS. This is equal to A inverse of. We have already calculated that sequence current IS, that equal to A inverse of I phase current IP. So if we use this relation where A is equal to this, if we calculate this, then what will be the IS equal to sequence component, means what is the sequence? This is a matrix. So sequence component current IS means what is? IS means I0, I1 and I2. This is my sequence component, that equal to A inverse means this one. This is 1, 1, 1, 1, 1, A square and A square A. And IP means ki, IP is another matrix. IP phase current matrix equal to how much? IA, IB and IC, right? This is the phase current matrix. So if we put this phase current matrix, then what we are getting? This is into, this is 1/3 into phase current IP equal to what? IA, IB and IC, right? Now IB, IC equal to IB, IC equal to 0. So both we can put 0, 0. And IA equals to how much we have got? IA equals to VAG by ZF, right? So this is equal to VAG by ZF. We have got this. From this, if we calculate, what we will get? I0, I1 and I2. We can calculate, you see, this is a 3 by 3 matrix and this is equal to 3 by 1 matrix. So this is equal to I0, this equals to 1/3 of, if you calculate this first row, first column, we are getting VAG by ZF, right? I0, I1 and I2, right? You are right over here. That equal to, this is a matrix, right? This is a single matrix, we multiply, then second row, first column, that is A, we can calculate VAG by ZF, VAG by ZF, and I2 equal to how much? This same way, it is 1/3, and then it is also VAG by ZF. If you calculate this thing, this, and because A square equal to, if you calculate 1 plus A square equal to 0. So if you apply this formula over here, then ultimately you will get this matrix. First row, first column means VAG by ZF. Second row, first column means this is VAG by ZF, this is 0, this is 0. And then this one is equal to how much? Third row, first column, this 1 into VAG by ZF. Then this is A square into 0, A into 0 means 0. So this is the 3 component you are getting. From this you will get I0 equals to 1/3 VAG by ZF, and I1 equals to 1/3 VAG by ZF, and I2 equals to 1/3 VAG by ZF, right? So you see both are equal. So that means from this we are getting I0 equal to I1 equals to I2. This is an important relation we are getting from this calculation. That means single line to ground fault for 3-phase balanced system, when it is subjected to a single phase to ground fault, zero sequence current equal to positive sequence current is equal to negative sequence current, that equals to 1/3 of VAG by ZF. Now we have seen IA, that equals to koto? IA equals to, we can write down IA equals to how much we have seen. So this is one of the relation we got, and now we can see VAG, a phase voltage to ground, VAG, that we can dissolve VAG, we can dissolve into 3 component. What are those 3 component? VAG equal to V0 plus V1 plus V2. We can write down in this way, VAG. So if we write down VAG equal to that means I1 equals to I2 equals to I0, that equals to 1/3 of VAG means this, right? V0 plus V1 plus V2, right? That is why 1/3 of, then here is a 1/3, one ZF is there. I1, I2, I0 equal to 0 equal to how much? V0 by 1/3 of ZF. So 1/3 VG means VAG means this is the VAG by ZF. If we put the VAG equal to this is the VAG. Then I1 equal to I2 equal to 1/3 of V. This is the VAG by ZF. So this is we are getting I1 equals to I2 equal to IT equal to 1/3 of ZF into VAG, right? Now you see here another way. This is one expression we are getting, and another expression we are getting I1 equal to I2 equal to I0. That means positive sequence current, negative sequence current, and zero sequence current are equal, and the voltage VAG, that means what the network we draw here, that VAG voltage with respect to ground, this is neutral. This is a connected through the impedance. If we consider these two terminal, that voltage is V0, V1, V2. These 3 voltages connected in series. These 3 V0 voltage, V1 voltage, and V2 voltage, if we connect in series, then we are getting VAG. And again, the current flowing through the current V0, current flowing through the V1, and current flowing through the V2, all are equal. So how that condition can be met? You see, very important observation here. there are two relations over here. One relation is zero sequence current, positive sequence current, and the negative sequence current are equal. That is one relation. Another relation, positive sequence voltage, negative sequence voltage, and zero sequence voltage, all if we connect all together if we sum up, then we are getting the phase voltage of A. That means when Fs to Fs is getting grounded, Fs voltage, this network when it is grounded, suppose that is the box. Okay. When it is getting grounded, that means when it is connected to ground through a neutral, what is happening inside? Inside we are seeing, if there is a voltage over here, suppose this is a voltage V0, this is a voltage V1, and this is a voltage V2. Like a battery, suppose this is one voltage. Okay, I withdraw like a battery. This is a one voltage. We are just for understanding, we are drawing this. Suppose there is a voltage over here. This is a positive, this is a negative. This is one voltage. Suppose this is positive, this is negative. Okay, this is a voltage V0. Then there is another voltage here. This is a negative, this is a positive. This is a V1. Then this is another voltage, negative, this is a positive, it is a V2. And this three is connected to this. If we do in this way, then zero sequence voltage, the voltage, what is the voltage difference between these two? What is the VAG? VAG equal to V0 plus V1 plus V2, because all are connected in series. Again, due to this, the current flowing through this is I0, the current flowing through this is I1, and the flowing current is I2. These three are equal. When that is possible? When a particular impedance, there are three impedances. When it is connected through a individual, when the current flowing through this same, suppose this current is I0, this current is I1, this current is I2. If all these three current are equal, that means it is flowing through the series connection. That means zero sequence network, positive sequence network, and zero sequence network all are connected in series, because this sequence network has a voltage V0, this sequence network has a voltage V1, this sequence network has a voltage V2. These three voltages are connected in series, and this impedance also in series. Then only it is possible all the currents are equal and it is flowing, and the voltage is sum of these three. That means from these two relation we can conclude, for single line to ground fault, all these three sequence network, zero sequence network, positive sequence network, and negative network, these three network are connected in series. That means there is a voltage source. Suppose this is a voltage source, the VF. So this VF, what is happening? This VF has a positive sequence, zero sequence network. Then it has a positive sequence network. Then it has a negative sequence network. Okay. This network, this is one box. This is another box. This is another box. Okay. The voltage difference between this box is V0 and the impedance is Z0. Okay. The voltage difference between these two is V1, impedance is Z1. The voltage difference between these two is V2 and impedance Z2. These three connected in series with a fault voltage, then that is drive a current in the outside. That is a VAG here, and that is connected what? We connected with the impedance of 3ZF. This current, you see, the current I1. This current is I0. Here current is I1. Here current is I2. All these three current are equal, and that current is flowing through this voltage, total voltage, sum of these three voltage over here, and there is a impedance of 3ZF. That means there is impedance connected over here, 3ZF. This is the equivalent circuit of these two relation. If these two relation is to be met, then that relation can be represented in the network. There is a fault voltage VF. VF equal to fault voltage, which is equal to VAG during the fault condition. This VF equals to, we can say, VAG during the fault condition. Okay. During that time, the fault condition, the current flowing through this here, I1 equals to I2 equal to I0. You can say any one of this. The current, this fault current component, phase component or negative component or zero sequence component, any of this component, that current is flowing through the voltage of VAG voltage, that is a fault voltage, through a impedance 3ZF when these three connected in series. So these two relation is give this picture. So from this we can calculate, that means IF fault current, that equals to how much? That equal to this 3 impedance, this fault current equal to this total impedance of this V0, right? VF, that is equal to VF by total network, this fault current in this circuit, this I1, that equal to our IF now. This fault current equal to how much? This VF divided by total impedance of the circuit. That circuit impedance how much? Z1 plus Z2 plus Z0 plus 3ZF, right? That is a I1, I2. This is I1, not IF. This fault current is following I1. That I1, any phase component which we previously calculated, V0, that is one third 3ZF. This can be represented in this way. So I1 equal to this fault voltage divided by how much? Z1 plus Z2 plus Z0 plus 3ZF. This is, we can write down I1 equal to this. So this positive sequence, or I2 or I0, whatever you want to write. Due to the single phase to ground fault, the positive sequence current, negative sequence current or zero sequence current, any one of this current equal to how much? The fault voltage divided by positive sequence impedance, zero sequence impedance plus negative sequence divided plus 3ZF. So that equal to the your phase component of the current. Then what will be the total fault current? Now the fault current equal to how much? We have write down over previously. Total fault current IF equal to how much? IF equals to, we have seen IF equals to how much? IF equals to zero sequence component plus positive sequence components plus negative sequence component, and we have seen all these three are equal. That means this equal to, I can write down 3I1 or we can write down this equal to 3I0 or this equal to 3I2. So if we represent the fault current in terms of the sequence component, fault current will be either 3I1 or 3I0 or 3I2. Now I1 equal to how much we have got? This is the we have got for IF. If we put this value of IF, then the fault current magnitude is terms of the sequence components of impedance equal to 3 times of IF. I1 means how much? VF by Z1 plus Z2 plus 3 Z0, here Z0 plus 3 ZF. This is the total expression. That means fault current equal to 3 times of voltage divided by zero sequence component, positive sequence component, negative sequence component plus 3 times, it is important, 3 times of neutral path impedance. That will be the fault current, total fault current for single line to ground fault in case of 3-phase power system under unbalanced condition. In a brief, we can write down, this is our final formula. When there is a single phase to ground fault, in a 3-phase balanced 3-phase system, the single line to ground fault will be how much? Single line to ground fault IF, that equals to 3 times of fault voltage 3 VF divided by zero sequence impedance plus positive sequence impedance plus negative sequence impedance plus 3 times of neutral path impedance. That will be the expression for single SL, single line to ground fault. Single line to ground fault, this is the formula. That means if we want to calculate the fault current for the asymmetrical fault or unbalanced fault, then we have to find out first from that network. We have to calculate what is the zero sequence impedance, what is the positive sequence impedance, what is the negative sequence impedance, and this value already was given in this. When we get this figure, then only we can calculate the fault current from this VF. VF means it is a fault voltage means equal to VAG, you can say. That is a phase voltage during the fault. Okay. So during fault we consider phase voltage, it is a normal magnitude, though it is slightly different. So by this expression, we can calculate the single line to ground fault. So now we can understand how important we have drawn one single line. That is, there is a generator over here. Then there is a transformer, there is a bus bar, then there is a cable, there is another transformer, then there is a motor. If we consider this network, for this network, suppose there is a fault over here. If we want to calculate the single line to ground fault, then what we have to do? We have to calculate the zero sequence impedance, positive sequence impedance, negative sequence impedance for the motor. Then we have to calculate the zero sequence, positive sequence, negative sequence for the transformer. We have to calculate the same for this cable, same zero, positive, negative for this transformer. Then we have to calculate for the generator. Then all the zero sequence component as per the fault position up to this point, these are connected in series. So zero sequence impedance of the generator, zero sequence impedance of this transformer, zero sequence impedance of this cable, zero sequence impedance of this transformer to be connected in series. That will give the overall zero sequence impedance for this network, which is this Z0. Then we have to calculate the positive sequence impedance, this positive sequence impedance, cable positive sequence impedance, this transformer positive sequence impedance. Sum of all these things will be the Z1A. Then similarly, you have to calculate the negative sequence impedance of this generator, negative sequence of this transformer, negative sequence of this transformer, negative sequence of this cable. Then we'll get the negative sequence impedance up to this point. That will get Z2A. Okay, and if we consider there is no fault, or suppose there is a resistance or impedance come of 0.2 ohm, then 0.2 ohm also to be added as a ZF equal to 0.2 ohm or 0.2 per unit, whatever the way. So when now we can put this figure over here, and we know the phase voltage. Suppose it is a 13.11 kV system. So 11 by root 3 is the phase voltage. 11 kV is the voltage of VF, voltage phase to ground voltage. So if it is 11 kV line to line, 11 kV by root 3 will be the phase voltage. That will be the phase voltage. You multiply it by 3 will give you the current for this system. So why we said that this sequence impedance of individual load is important to calculate the short circuit current, that get clear from this expression. So whatever the demonstration we have given in the slide number 59, video number 59, that is very, very important to calculate the short circuit current for asymmetrical fault, because we have shown how to calculate the zero sequence impedance, positive sequence impedance, negative sequence impedance for the various type of load that we have discussed last part of video number 58 and the entire video of 59. So if you want to have a clear idea about the short circuit current due to unsymmetrical fault, then you must go through the video number 59 and 58. Then only it will be clear how to calculate this sequence current. So this is the master formula for single line to ground fault short circuit current calculation. This way we have calculated this relation, in the same way we can calculate the relation for line to line fault and double line to ground fault. I am not going for the detailed calculation for those two relations. I will just write down those two relations over here, but you can keep in record, and if you want to calculate you can do, and you will get the same result. In case of double line to ground fault, or suppose line to line fault, in case of line to line fault, if you want to calculate the fault current, you will get that fault current equal to, in case of line to line fault, yeah, it is not the arc fault, it is a phase fault. Line to line fault means between two phase fault. Suppose this is a network, this is a network, this is A phase, this is B phase, this is a C phase. Okay, A phase, this is a B phase, this is C phase. There is a fault over here between these two, like this. In that case, whatever the fault current flowing through this IF, that equals to how much? That will be equal to root 3 of the voltage, fault voltage BF, divided by positive sequence impedance plus negative sequence impedance plus zero sequence impedance. That will be the expression for this fault. Okay, zero sequence fault is not, it is a face to face fault. So it will be coming, the impedance coming in the fault path into ZF. Because there is no arc fault over here, so zero sequence voltage will not come into the picture. So voltage, the formula for fault will be root 3 into angle will be the voltage. If the voltage is not the zero angle, corresponding angle will be coming over here. It is a minus 90 degree. You can say this formula is minus 90 degree. So in case of arc fault for line to face fault, the fault current will be root 3 into BF by Z1 positive sequence impedance, negative sequence impedance, and the fault path impedance ZF. That will be the formula. In case of double line to ground fault, if we go, the fault current will be different. In that case, I fault, it is a line to ground fault. In that case, I fault current, that will be simply 3 times of at fault current I0. If we calculate the single line to ground, what was the fault current I0? 3 times of I0 equal to the at fault current in case of line to line ground fault. So these are the another two relation which we can drive in the same way. Okay, but it will take more time to calculate. That's why I am not going to calculate this thing. I have shown one calculation, all typical calculation for line to ground fault. The same way, if we apply the same way over here, we will get it for line to line fault. The at fault current will be root 3 into Vf into angle of minus 90 degree by Z1 plus Z2 plus Zf. Zf is the fault path impedance and Z1 and Z2 positive and negative. And in case of line to ground fault, I am equal to 3 type of I0. We can calculate the I0 in the same way as the line to ground fault. So these are the three formula for calculating the three type of fault current. So with this we are closing this video. Now next video we will take one the same practical example which I have shown in the network. For that particular network or similar network, we will calculate this three type of fault current with a physical example. How exactly we will draw the equivalent network, and then from that equivalent network we will calculate the equivalent fault current for the line to ground fault, double line fault and line to ground fault. Actual calculation how much ampere fault current is flowing in three cases, that will show in the next video, video number 61. So with this we are closing today, and thank you very much for your sharing, for your cooperation and sharing with this channel. Keep it up and we'll be proceeding in this way. Thank you very much indeed. Thank you.